Because the dehydration reaction is not observed to occur at 298 Kelvin, the student claims that the reaction has an equilibrium constant less than 1.00 at 298 Kelvin. Do the thermodynamic data for the reaction support the student's claim? Justify your answer, including a calculation of standard or change in standard Gibbs free energy at 298 Kelvin for the reaction. So first of all, let's review what the student's claim is. The student claims that since the reaction is not observed at 298 Kelvin, that at that temperature, the student claims that the reaction has an equilibrium constant less than 1.0 at 298 Kelvin. That's their claim. And if the ideas of equilibrium constant or Gibbs free energy are completely foreign to you, I encourage you to review the videos on Khan Academy on Gibbs free energy and equilibrium constants. If they're familiar to you, but you're like, okay, I don't know all the formulas that might connect the information that's given in the problem and how to calculate delta G, and maybe how do we go from delta G to equilibrium constants and figuring out whether equilibrium constant is going to be greater than or less than 1 or equal to 1. The good thing is that they give you all of the formulas that you need. It's on the first page of the free response section. You just have to understand which ones are applicable and what's actually going on with those equations. So let's first of all think about whether we can, let's think about whether we can calculate delta G with the information that they've given. And if you go to the first page on one of the formulas, they give you, and you might even remember on how do you figure out whether a reaction is spontaneous or not, and how you can calculate delta G based on the temperature, the change in entropy, and the change in enthalpy. You have this formula right over here, and I literally just copied and pasted it from what they give you when you take the test. And so they give us the change in enthalpy for the reaction. They give us the temperature, 298 Kelvin. They give us the change in entropy for the reaction. This is the change in standard entropy, change in standard enthalpy for the reaction. And so using those, we can figure out what delta G is going to be. And then we can say, okay, is it consistent? Is it greater than 0, which is consistent with the reaction not being spontaneous, which seems to be what's observed? And then how can we go from that delta G to the equilibrium constant? Well, they also tell us that delta G is equal to this second thing, and this connects delta G and the equilibrium constant. And we know some things about R and T. In fact, we know exactly what R and T are if we need them. So let's go ahead and apply these equations right over here. So you have, actually, let me just write all the information we have first. So what is our change in standard enthalpy? We have to figure that out. We're going to have to figure out what our change in standard entropy is going to be. We know what the temperature is. We know that that is 298 Kelvin. And we could worry about R in a second if we need to. So up here, when they gave us the reaction, they gave us our change in standard enthalpy and our change in standard entropy at 298 Kelvin. This is very convenient. So our change in enthalpy is 45.5 kilojoules per mole. Our change in standard entropy is 126 joules per Kelvin mole. So this is very interesting. This is given in kilojoules. This is given in joules. And so we want to make sure that we're being consistent. So let's just make sure everything is in joules. So I'm going to write this. This thing is the same thing as 45,500 joules per mole for this reaction. So let me write this down. This is 45,500. This is 126 joules per Kelvin mole. So this right over here is 45,500 joules per mole. This is 126 joules per Kelvin mole. And now we can figure out what the delta G is going to be. The delta G is going to be equal to, well, our change in enthalpy is 45,500 joules per mole minus our temperature, 298 Kelvin, times our change in entropy, times 126 joules per Kelvin mole. And notice the Kelvin and then the Kelvin, those should both be capital K's. This is a capital K. Cancel out, and the units here are going to be joules per mole. The units here are going to be joules per mole, and then we just figure out the difference. So let's do this. Let me get my calculator out. And so this is going to be This is going to be, well, let me multiply these two first. You're going to have 298 times 126 is equal to that. And let's see, I'm going to subtract this from 45,500. So let me just make it a negative and add it to 45,500 is going to be equal to 7,952. And if we want to stay, and we want to stay consistent with how many significant digits or significant figures we have, and it looks like it's pretty consistently 3 significant figures, so we want 3 significant figures here. So we could write 7,900, roughly 7,950. So our delta G is approximately 7,950 joules per mole. And the fact that this is greater than 0 tells us that this is not going to be spontaneous at that temperature. So it's already consistent with our observations. And that's always a good reality check, is are the things that you're seeing consistent with what the question is describing. So delta G greater than 0, consistent with reaction being, or not being spontaneous, spontaneous at 298 Kelvin. And we, in the videos on Khan Academy on Gibbs free energy, we go into a lot more detail on what this is. But one way to think about it is, this is the energy, the change in energy that's available to do work. And so if you have more, if your Gibbs free energy increases over the course of the reaction, that means the products have more energy to do work. And that means you have to put work into it in order for the reaction to actually proceed. If your delta G is negative, that means your products have less energy to do work than your reactants, which means that it can release that energy and it can do work and it can be spontaneous. So this one, it's greater than 0, so it's not going to be spontaneous. But that doesn't answer the question for us. We want to validate the claim that the reaction has an equilibrium constant less than 1 at 298 Kelvin. And lucky for us, they also give us the formula that ties our delta G to our equilibrium constant. And we know the other things. We know R and we know T. And we might not actually even have to think about them, because they're not even telling us to calculate the equilibrium constant. They're just saying we'll validate that it's going to be less than 1. And so if we took 7,950 joules per mole is equal to negative RT times the natural log of our equilibrium constant, we'll solve for the equilibrium constant. Let's see, if I divide both sides by negative RT, I'm going to get the natural log, let me just write it this way, the natural log of my equilibrium constant is going to be equal to 7,950 joules per mole over negative RT. Or you could say E, this is just what power do I raise E to get K? Or so you could say E to the negative 7,950 joules per mole over RT is going to be equal to K. And we could actually calculate what this is. We know which R to use. We're dealing with joules and moles. So it would be this first gas constant right over here, 8.314 joules per mole Kelvin. But we actually don't even have to do that, because we just have to validate that K is going to be less than 1. What happens if you raise E to a negative exponent? And this is going to be a negative exponent. This is positive. That is positive. This is positive. We know it's 298 Kelvin. Positive. So my entire exponent is going to be negative. So negative. So you could say that K equals E to negative number. Or I could just write, it's kind of weird to write the negative and then the negative number. E to a negative number, which must be less than 1. Remember, if the exponent is 0, e to the 0 power is 1, e to anything positive is going to be greater than 1, and e to anything negative is going to be less than 1. Let me be careful, not less than 0. You actually can't get to less than 0. It's going to be less than 1. And so this by itself already validates the student's claim. If you want to go further, you could just calculate that. You could just say K is equal to e to the negative 7,950 joules per mole over R, which is what, 8.314 joules per mole Kelvin. 8.314 joules per mole Kelvin times 298 Kelvin. Those cancel out. And joules per mole divided by joules per mole, those cancel out. And so you would get your number. And actually, let's just calculate it, just for kicks, just to really feel good about it. And you can see this is going to be dimensionless, and equilibrium constants are dimensionless. And so we are going to get, this is kind of fun. So let's see, let's do this denominator first. If you have 8.314 times 298, that's going to be equal to that. Now we're dividing by that, so let me take the reciprocal of that and multiply it by 7,950. 7,950 is equal to that. Now we want to raise e to the negative of that, so let's make that negative. And now let's raise e to that power. So let's see, we can raise e to that power. So we just press that, and there you have it. This is approximately 0.440, I guess you could say. So this is, or 40, well, let's just say 404. So this is approximately 0.404. Approximately 0. Wait, I already forgot the number. I have a bad memory. 0.0404. 0.0404. And the whole rules of significant figures get a little bit trickier when you're starting to deal with exponents like this. We're not going to, and they don't ask us to actually calculate the exact value, but hopefully this makes you at least appreciate that the equilibrium constant is for sure is less than 1. Aluminum metal can be recycled from scrap metal by melting the metal to evaporate impurities. Calculate the amount of heat needed to purify 1 mole of aluminum originally at 298 Kelvin by melting it. The melting point of aluminum is 933 Kelvin. The molar heat capacity of aluminum is 24 joules per mole Kelvin, and the heat of fusion of aluminum is 10.7 kilojoules per mole. All right, so we need to think about the heat needed to raise its temperature from 298 Kelvin, to raise the temperature of this 1 mole of aluminum from 298 Kelvin to 933 Kelvin. And we're going to do that by looking at the molar heat capacity. And then we need to add to that the heat of fusion, the heat necessary to actually melt it. So let's do that in steps. So heat needed to raise temperature by how much are we raising the temperature by? We're going from 298 to 933. So see, if you raise by 2, you get to 300, and then you have to raise by another 633. So that's going to be, so we're raising our temperature by 635 Kelvin. That's to get us to the melting point. So the heat needed to raise temperature by 635 Kelvin. Well, we have 1 mole of aluminum. I can write 1.00 to show that we have 2 significant digits, or 3 significant digits there. 1 mole of aluminum times the specific, or the molar heat capacity, I should say. So 24 joules per mole Kelvin times, so this right over here would be the amount of heat to raise it by 1 Kelvin. But now let's multiply by, we have to raise it by 635 Kelvin. 635 Kelvin. And the units work out. Moles cancel with moles. Kelvin cancels with cancels. Kelvin cancels with Kelvin. And then we get to, let's see, let me get my calculator out here. So 24 times 635 is equal to 15,240. And we're taking the product of a bunch of stuff, 3 significant figures, 2 significant figures, 3 significant figures. So we should write only 2 significant figures. So we'll round to 15,000 joules. So this is going to be 15,000 joules just to raise the temperature to 933 Kelvin. And then we have the heat of fusion, heat to melt once at melting point. Well, that is going to be 1 mole times the heat of fusion times 10.7 kilojoules per mole. So this is going to give us 10.7 kilojoules, or if we want to write it in joules, so this is 10.7 kilojoules, which is equal to 10,700 joules. And so the total is going to be the sum of these. So we could say it is 25,700, but we only have 2 significant figures here, so we could round that. And so we could say 26,000 joules, or I guess we could write 26 kilojoules. All right, now part B. The equation for the overall process of extracting aluminum from aluminum oxide is shown below. All right, is shown below. Which requires less energy, recycling existing aluminum or extracting aluminum from aluminum oxide? Justify your answer with a calculation. All right, so this reaction right over here, and this gives us the heat necessary for a mole of the reaction. So if you get a mole of aluminum oxide, you put in this much heat, you're going to get 2 moles of aluminum and 1.5 moles of molecular oxygen. So the equation, so let's see, the equation for the overall process. So to extract 1 mole of aluminum from aluminum oxide requires, so this much heat will produce 2 moles. So to do 1 mole, you just have to have half of that. It requires 1,675 kilojoules divided by 2. So this is going to be 1,675 divided by 2 is equal to, let's see, it's going to be 837.5. 837.5 kilojoules. Yep, that's half here, and I had 4 significant digits here, and I still have 4 significant digits. Extracting, doing it from, which requires less, recycling existing aluminum or extracting it? Well, to recycle 1 mole requires, we just figured out, 26 kilojoules. 26 kilojoules. Everything here is in kilojoules, which is much less energy. And we are done.